Here we go. So I want to break this talk down into basically three categories, right? So first one, tDCS, current mapping, and then the kind of results we got in vivo. Cool. So tDCS, I'm not going to talk a lot about it. I think people, I'm just going to breeze through this section. It's basically, we put sponge electrodes on the head, we apply a DC current, that's tDCS. Mechanism, basically just based on like single neuron, you have a resting potential and a threshold. You go above the threshold, you get an action potential. tDCS just basically moves your resting around, good, I have a pointer. It also moves your resting closer to the threshold to make it easier to fire, or away from the threshold, making it tougher to fire. Effects, there have been tons of effects, cognitive enhancement, also clinical effects. So if I were to sum up like why I guess clinicians are super interested in this, then it's because like they have this one solution which is kind of expensive and has side effects, and then they look at this and they say, hang on a sec, I can just use a battery, So that's what got me started into this. I did like a quick PubMed search. There's a lot of interest, more than a paper a day last year, with tons of publications in stroke, pain, depression. And the problem I was trying to address was where does the current go? So let's get into it. So current mapping. So basically it's based on two principles. So the first one is that the electrical current creates a magnetic field. And how does that work? So that's based on Ampere's law. There's like a jumble of mathy stuff here, but what I want you to take as a take-home message is that the electrical current generates a linear magnetic field. Okay. The second principle is that the MRI can detect magnetic fields. Okay, so how does that work? So this is our generic MRI with the generic stick figure man, totally realistic in there. And the first thing we do is replace the man with a bunch of protons, because people are protons in an MRI. And the way it works is basically the protons spin at a frequency. The field deviations change this frequency. So if you have a larger field, they spin faster. If you have a smaller field, they spin slower. And these frequency changes can be detected by an MRI using field mapping. So just to kind of like recap, our first thing we looked at was electric current creates a magnetic field. That was the Ampere's law. This magnetic field changes BZ field, and this change BZ field can be detected using MRI field mapping. And that's kind of like a representative image. Looks really crappy, by the way. So how do we do the experiment? Well, basically, we apply a current, measure a field map. We do that for a bunch of more currents. One of the challenges we faced in this was that, the field measurements would drift over time. And our solution was to basically interleave sort of like baseline or control scans in between. And that's basically just a no current scan, and we just interleave them. And this whole bunch of scans we group together as our real block. And we also have a sham block where we don't apply the current, but we do the same acquisition. So this is kind of like our control. Just to summarize, the applied currents, the order of the applied currents was pseudo-random and counterbalanced. And the duration of current was, well, for sham, we switched it off after 20 seconds. For real, we kept it on. Okay, so now that we have the data, how do we process it? So basically, we look at the data voxel-wise, and we use a modeling to remove the baseline effects that we measured through the baseline scans to get the field due to current and leave the confounds out. If we think about the field due to current versus the applied current, then we expect the relationship to be linear from Ampere's law, because electrical current generates a linear magnetic field. And so we can use this. This is sort of like the crux of it. We can use this as a test. If in a voxel, if we find the relationship to be linear, we're going to say it's due to current. If not, then, and so this brings us to our test statistic. And so we end up picking Pearson correlations. And this just basically is to do this linearity test of sorts. And so after all of this, we basically end up with like a correlation map for one experiment. if we have a bunch of participants, we have more than one correlation maps, and we can think about doing a group level analysis and asking the question, what are these consistent subject-wise correlations? So moving on to the results, I have the first one up is a phantom, and the motivation here was that let's fix the current path so that we know exactly where the current is going, and then let's see what the method tells us. So that's the motivation. So what we did was basically just took a tube of conducting saline, stuck two electrodes in it, current flows from the red to the black. This is like an axial view. If I do a sagittal cut, then I see a cross-section. Really nice. The other thing we did was that we wrapped it around like your generic plastic MRI phantom. So it kind of looks like this. A little messy, but it works. So, and then we stick it in the scanner. So this is our final like view of the phantom in the scanner. And so the reason I went over a little bit over the construction was because I wanted to build up intuition about what kind of results do we expect when we do this experiment. So let's just quickly look at that. We just did one experiment for this. So this is our phantom in the scanner. The current flows into the screen here. So it turns out that the magnetic fields are really nicely formed. They kind of look like this. And just as a physics side note, the arrows only depict the direction and not the magnitude. The magnitude actually goes down from the center, the farther you are. But we have fields like this, and we only detect changes along our BZ field. So let's get rid of the components that are not along BZ. So that makes it look like this, kind of. And now we see a pattern here, which is so we have like a sort of like an equator, and above it we have all the fields pointing opposite from B naught, and below it we have all the fields pointing along B naught. So, in this region, the net field is going to be more than V naught, and here it's less, sort of. And so the intuition I'm driving towards is if I apply a current, I should see a field that's more than B naught here, less than B naught in the blue region. If I keep applying higher currents, it becomes more positive, like more greater than B naught, more lesser than V naught. And so the intuition I'm building towards is that the fields over here will be positively correlated with the increasingly applied current, and the opposite on the top. And we're here almost. So let's check out the measured results. And we do see something similar here, which is kind of predicted of here. I'm going to move on to the next experiment, which we did on a calf, where the electrodes were placed laterally. Again, the data was acquired from one person. Well, let's leave this for later. And so we're going to again look at what do we expect from an experiment like this. And so we just have our old model from the previous slide with a couple of changes. There's no conducting tube that's carrying the current in your calf, so let's get rid of that. The hypothesis is similar, that the current is going to flow along the surface, hopefully. So we just kind of copy and paste that correlation structure here. And last but not the least is that third point is that the current was traveling in the opposite direction. The fact that the current is, like the sign of the current is switched, basically implies that the sign of the correlations will also be switched. So we expect something like this. And let me just make it larger here. And the measured results were kind of pretty similar, I guess. We see a correlation around here, and they were cluster corrected, all that good stuff. The last experiment was when we did it on the head. The electrodes were placed bilaterally on the motor cortices. Data was acquired for 12 people. Scanning protocol was identical. And then, so we get a correlation map for each subject. And so the group level analysis involved doing a one sample t-test on the subject correlation maps, with the hypothesis being like across the group there should be no systematic correlation on either side. And that kind of brings us to the results. So the sham on the left, real on the right. I have been analyzing this over the past 1 month, and the results in the orbitofrontal are a little unstable, so I'm not exactly sure. But the results under the electrode are, I'm pretty sure, they're very stable. there. And yeah, there's some scattered sham effects, but I think I'm still looking at it right now. And yeah, I would like to acknowledge there were a bunch of people without whom this work, I mean, I don't think I would have been able to do it. And I would love to take any questions if you have.